In episode 59, titled Environmental Requirements, Temperature, Humidity, BTUs, and Failure Prevention, the focus is on environment as a slow risk that can quietly build for weeks and then present as a sudden, ugly failure at exactly the wrong time. Environmental control is easy to deprioritize because it feels like facilities work, yet it directly determines the reliability of network and compute gear. The exam tests this topic because environmental problems often masquerade as random technical faults, and because basic concepts like heat load and humidity thresholds are foundational to uptime. When you understand environmental requirements, you can prevent outages that would otherwise look like mysterious link flaps, server crashes, or storage errors. Temperature, humidity, and airflow do not just influence comfort, they influence component tolerances, power stability, and long-term equipment life. The goal here is to connect the physical realities to the operational controls that keep infrastructure stable. When you can reason about environment the way you reason about redundancy, you are designing for failure prevention rather than reacting after the fact. Before we continue, a quick note: this audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Temperature limits matter because heat accelerates wear, increases error rates, and shortens equipment life even when devices appear to be functioning normally. Semiconductor components, power supplies, and storage devices all have operating ranges, and operating near the top of those ranges reduces reliability over time. Heat increases electrical resistance and can cause components to run hotter still, creating a feedback loop where cooling becomes harder and failure becomes more likely. Even before outright failure, heat can cause performance throttling, fan overrun, and intermittent faults that appear as unstable behavior in the network. The exam often expects you to recognize that overheating can produce symptoms like random reboots, packet loss, and interface errors, not just complete shutdown. Heat also stresses capacitors and power components, which can lead to failures months later, long after the initial temperature problem was fixed. This is why temperature management is not only about avoiding a crisis today, but also about preserving equipment health for the future. When you treat temperature as a controlled variable, you reduce both immediate outages and long-term degradation. Humidity extremes are another environmental risk because both low humidity and high humidity can cause distinct failure modes. Low humidity increases static electricity risk, which can lead to electrostatic discharge events that damage sensitive components or cause intermittent faults during handling and maintenance. High humidity increases condensation risk, especially when temperatures fluctuate, because moisture can form on surfaces and create short circuits or corrosion. Condensation is particularly dangerous when cold air meets warm equipment or when HVAC cycles create temperature swings, because moisture can appear where it is least expected. The exam often tests this by implying humidity problems through symptoms like corrosion, unexplained failures after cooling changes, or issues during seasonal transitions. Proper humidity control reduces both static and condensation hazards, making equipment behavior more predictable. Humidity is also easy to ignore because it does not always show immediate symptoms. Yet, it can be a slow destroyer through corrosion and contamination. Understanding humidity extremes helps you see why environmental monitoring must include more than temperature alone. British thermal units, commonly called BTUs, represent heat output and are used for cooling sizing, which ties directly into how much equipment a space can safely support. Heat output is essentially the byproduct of power consumption, because most of the electrical energy used by devices becomes heat. BTUs provide a practical way to quantify that heat, so cooling systems can be sized to remove it and maintain stable temperatures. When you add equipment to a rack, you are increasing heat load, and if the cooling system cannot remove that additional load, temperatures will rise even if airflow appears normal. The exam expects you to recognize that cooling capacity must match heat output, and that planning must consider both current load and growth. BTU thinking also helps you understand why a space can be fine at low utilization and then fail under peak load, because power draw and heat output rise when systems are busy. If cooling is sized only for typical load, peak periods can push temperatures into unstable ranges. When you connect power, heat, and cooling through BTUs, environmental planning becomes a capacity planning discipline. Continuous monitoring is essential because environmental drift is often gradual and because spot checks miss transient spikes and failure precursors. Spot checks might show a room is within range at a single moment, while the environment swings outside safe thresholds overnight, during HVAC cycling, or under peak compute load. Continuous monitoring provides trend data so you can see creeping temperature rise, humidity swings, or abnormal patterns that indicate failing cooling components or blocked airflow. Monitoring also enables alerting, which is crucial because environment problems often require rapid response to prevent cascading failures. The exam frequently expects you to choose continuous monitoring over occasional manual checks, especially for critical spaces like main distribution frames and server rooms. Monitoring should include sensors placed where problems show up first, such as hotspots in racks, return air pads, and areas near doors or vents where mixing occurs. Continuous data also supports post-incident analysis because you can correlate device faults with environmental changes rather than guessing. When you monitor continuously, environment becomes measurable and manageable rather than mysterious. Airflow planning is a conceptual principle that matters even when you are not designing a full data center because equipment cooling depends on predictable air movement. Hot aisle and cold aisle principles describe separating cold supply air from hot exhaust air so that devices intake cool air consistently and do not recirculate their own heat. Conceptually, cold air should be delivered to the fronts of devices, and hot air should be removed from the backs, keeping intake temperatures low and stable. When airflow is poorly managed, hot exhaust can mix back into cold intake, raising temperatures at the equipment, even if the room temperature sensor looks acceptable. Airflow also depends on rack layout, blanking panels, cable management, and avoiding obstructions that disrupt flow paths. The exam often tests this concept by describing hotspots or device overheating in a room that feels cool, which is a clue that airflow and recirculation are the real issues. Hot aisle and cold aisle thinking helps you understand that cooling is not just about making a room cold, but about delivering cold air where equipment actually draws it. When airflow is planned, cooling efficiency increases and temperature stability improves. A realistic scenario is clogged filters raising temperatures and causing link flaps, which illustrates how environmental issues can present as network instability rather than as obvious thermal alarms. As filters clog, airflow decreases, causing cooling systems to deliver less effective cooling and causing intake temperatures to rise gradually. Network switches and routers may respond by increasing fan speeds, but if intake temperatures continue rising, components can become unstable and interfaces may begin to error. Link flaps can occur because physical layer components are sensitive to thermal stress, and brief drops can look like cabling issues or upstream instability. This is why environmental problems are often misdiagnosed, because engineers see symptoms at the network layer while the root cause is reduced airflow and rising temperature. Continuous monitoring would show the temperature trend, and maintenance schedules would prevent filter conditions from reaching that point. The exam expects you to recognize that recurring link instability combined with rising temperature indicators points toward environmental root causes. When you connect the symptom to airflow and cooling, you can prevent repeated incidents by fixing the underlying condition rather than chasing phantom network bugs. A common pitfall is placing gear in closets without adequate ventilation, which turns a small enclosed space into a heat trap. Closets often lack dedicated cooling, proper airflow paths, and environmental monitoring, and they may be used because they are convenient rather than suitable. When equipment is placed in such spaces, heat builds up quickly, especially under load, and the environment can swing outside safe limits without anyone noticing. Humidity can also be uncontrolled, and doors being opened and closed can create rapid changes that increase condensation risk. The exam tests this because it is a frequent real-world failure pattern, and the correct answer emphasizes proper environmental controls rather than assuming small spaces are safe by default. Even a modest amount of equipment can overwhelm a closet's ability to shed heat, leading to throttling, reboots, and premature hardware failure. Once the space overheats, recovery may require cooling it down, which can take time and prolong downtime. The key is that ventilation and cooling are capacity constraints, and closets rarely have sufficient capacity for critical gear. Another pitfall is ignoring seasonal changes and HVAC maintenance windows, which can cause predictable outages during transitions and planned work. Seasonal changes affect ambient conditions, humidity, and cooling efficiency, and spaces that are stable in winter can overheat in summer as outside temperatures rise. HVAC maintenance windows can also reduce cooling capacity temporarily, and if that reduction is not coordinated with IT operations, critical equipment may be exposed to higher temperatures and humidity swings. The exam expects you to recognize that environment is dynamic and that planning must account for changing conditions over time. Maintenance windows are planned events, but they create planned risk, similar to patch windows, and must be designed around. If a cooling unit is taken offline for service, remaining units must carry the load, and if they cannot, temperatures will rise. This is why coordination between facilities and IT is operationally critical, because facilities' actions can directly affect system uptime. When you plan for seasonal and maintenance impacts, you reduce the chance of sudden failures that were actually predictable. Quick wins include setting thresholds, alarms, and maintenance schedules, so environmental drift is detected early and root causes are addressed before failures occur. Thresholds should reflect equipment intake limits rather than only room averages, because hotspots at the rack can exceed safe ranges even when the room is acceptable. Alarms should route to people who can act quickly, and they should be tuned to avoid alert fatigue while still catching meaningful excursions. Maintenance schedules should include filter replacement, HVAC inspections, and cleaning routines that prevent airflow degradation and dust buildup. These actions are practical because they reduce risk without requiring major facility redesign, yet they can prevent a large share of environment-driven outages. The exam often rewards answers that include preventive controls because they reflect a real operational approach to reliability. Environmental failures often have early signals, and thresholds and alarms turn those signals into action. When you combine monitoring with preventive maintenance, you shift from reactive incident response to failure prevention. Operationally, coordinating facilities and IT for incident response is crucial because environment incidents require both technical and physical actions. If IT observes rising temperatures and device instability, facilities may need to adjust HVAC settings, open or close vents, address failed cooling units, or bring in temporary cooling. IT may need to reduce load, shift workloads, or shut down non-critical systems to reduce heat output while cooling is restored. This coordination should be planned in advance, with clear contact paths, escalation steps, and shared understanding of which spaces and racks are most critical. The exam expects you to recognize that environmental resilience is cross-functional, not purely technical, because the best monitoring in the world does not help if no one can act when alarms fire. Incident response must include both containment actions and recovery actions, such as restoring cooling and verifying stable conditions before resuming full load. Post-incident review should include environmental data so root causes are documented and preventive actions are scheduled. When facilities and IT work as one team, environment becomes controllable during crises rather than chaotic. This collaboration reduces downtime because response is faster and more targeted. A useful memory anchor is heat, humidity, airflow, alarms, maintenance, because it captures the elements that prevent environment issues from turning into outages. Heat reminds you to control temperature because it shortens equipment life and increases failure probability. Humidity reminds you to avoid extremes that cause static and condensation risks. Airflow reminds you that cooling depends on how air moves through racks and rooms, not just on thermostat readings. Alarms remind you that continuous monitoring and alerting are required because spot checks miss drift and spikes. Maintenance reminds you that filters, HVAC systems, and airflow paths degrade over time and must be maintained proactively. This anchor is especially helpful on the exam because it turns a broad topic into a clear checklist of factors to evaluate in a scenario. When you apply it, you can diagnose why a room that should be fine is still causing device instability. It also connects environmental factors to operational controls, which is the level of reasoning the exam expects. To apply the concepts, imagine being asked to diagnose symptoms consistent with overheating equipment and focus on patterns that indicate thermal stress rather than isolated errors. You might see fan speeds running high, devices reporting thermal warnings, and intermittent link flaps that appear during peak load or at certain times of day. You might see increased error rates, random reboots, or performance throttling that resolves temporarily when load drops or when doors are opened and cool air mixes in. You would correlate these symptoms with temperature sensor trends, looking for rising intake temperatures, hotspots in specific racks, or spikes that align with HVAC cycling. You would also examine airflow constraints, such as blocked vents, missing blanking panels, cable obstructions, or clogged filters that reduce cooling effectiveness. The exam expects you to connect symptoms to environmental causes and to propose monitoring and maintenance fixes rather than only swapping hardware. When you can explain why the symptoms fit overheating, you demonstrate understanding of how physical conditions manifest as network and compute instability. To close episode 59, titled Environmental Requirements, Temperature, Humidity, BTUs, and Failure Prevention, the essential point is that environment is a slow-moving risk that becomes sudden failure when thresholds are crossed. Temperature control matters because heat shortens equipment life and increases instability, while humidity control matters because extremes create static discharge and condensation risks. BTUs quantify heat output and drive cooling sizing, linking power consumption to environmental capacity. Continuous monitoring is necessary because spot checks miss drift and spikes, and airflow planning concepts like separating hot exhaust from cold intake prevent recirculation and hotspots. Real-world failures can appear as link flaps and random reboots, especially when filters clog or ventilation is inadequate. And these symptoms must be interpreted through the environmental lens. Seasonal changes and HVAC maintenance windows create predictable stress events that require coordination between facilities and IT. Your rehearsal assignment is an environmental checklist rehearsal where you state the thresholds you would watch, the alarms you would expect, the airflow checks you would perform, and the maintenance tasks you would schedule, because that rehearsal is how you convert environmental awareness into failure prevention. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.